Yes, and we're back for the second hour, part 3 of chapter 21, going through the key reactions. Don't forget about these things due tonight and tomorrow there. We're starting now our 4th reaction in this chapter. Remember, I said there are 6. This is enamine formation now. So an enamine is different in that we have a secondary amine, 2 alkyl groups on the nitrogen, either an aldehyde or ketone. And one of the requirements here, you have to have at least one alpha hydrogen, one hydrogen next door on the adjacent carbon to the carbonyl. And you'll see mechanistically why that is, requirement-wise. And also the product is different. The 2 alkyl groups on the amine are still there, on the enamine product now. And then the alkene, that's part of the name, the enamine, the ene refers to the alkene right here. It's a carbon-carbon double bond right there. And again, we'll lose water here. That's part of the driving force. Again, if we have a little bit of acetic acid, in there it will go. If we have too strong of an acid, if we have an equivalent of HCl, for example, the reaction won't go. Or if we have too much base in there, it won't go. It will go at neutral pH if it's just pH 7, but if it's slightly acidic here, that's where you'll get the best reactivity to go. So you can have that there or leave it off, either way, okay? If you just show an aldehyde or ketone with a primary secondary amine in this case, and don't show the acid, you still get these products. Let's show a couple other examples of this. So you can have a ketone here, and you can have pyrrolidine. There's pyrrolidine, which is also a secondary amine, and we're going to get the double bond right there, and the cyclic amine up here. This is a secondary amine, right? 2 carbons are on there, and there's at least 1 alpha hydrogen to remove here. We'll see how we eliminate water in that case. How about if we go back to an aldehyde here, propanal, and react it with this secondary amine. This is called morpholin, which is a 6-membered ring and an ether oxygen here, but because it's secondary amine, this will give us this product here. Now it looks kind of funny, but again, you have the double bond right here at the alpha position and where the carbonyl was, and then the secondary amine going along for the ride. How about a ketone, acetophenone, and diethylamine? Okay, so what will be that product? We'll have the double bond there and the nitrogen with the 2 ethyl groups there. Okay, so that gives us that type of product. There's one I want to point out here that shows a limitation. What if we have this carbonyl compound? It's an aldehyde, but look, benzaldehyde, there's no alpha hydrogen here. The carbonyl's directly on the benzene ring. So what about this? If this was a primary amine, that would be okay. But if this is a secondary amine, say it's diethylamine, what can happen here? Well, you're going to get to this point of the reaction, and you can eliminate water, but look, you can't put the double bond here. This is the aromatic group. You'd break aromaticity. Try to put the double bond here. So if you don't have an alpha hydrogen, or if this is a tertiary amine, it's fully reversible and will not give the enamine or an imine product, okay? So you need a secondary amine with a carbonyl compound, aldehyde ketone, that has an alpha hydrogen on it, okay? So let's get to the mechanism here. Let's do a class activity sheet. If you can look back up here to the overhead. This is on a sheet you can get, again, on Learning Suite there, but here's the challenge. Okay, enamine formation involves secondary amine, aldehyde, or ketone. Write a mechanism for the reaction. Again, we got to do electron pushing that justifies the double bond in this case, and explain the difference between primary and secondary amines. Indeed, this is a secondary amine. That's that pyrrolidine. You don't need to worry about the name for that. And that's an example I just showed you, and it forms the enamine. And then explain why tertiary amines will not form. And also, let's see, why is the reaction faster at pH 5 with a little bit of acetic acid? Okay, and what happens when they're treated with acid water? Well, we already talked about this in the case of the imines. They reverse back to the aldehyde of the ketone. So let's pause your video and work on that for a second. And we are back. Let's see the mechanism here. So what are we going to do? Let's start out with the protonated aldehyde again. And let's go ahead and attack with the lone pair on the amine. So it's our nucleophile with our electrophile, right? So that part's the same. And then we get to this point, we get the alcohol amine. But the amine, remember, still has this hydrogen on it, so it's plus charged, right? So that's your overall plus charge. Now we can transfer the proton here. That will give us the hydronium cation and the neutral amine down there, okay? And then just like before, we can eliminate water now, right? And we can have the carbocation here, or let's just go ahead and bring the pair of electrons in here. Now that will just be a resonance structure of doing it stepwise, but what do we have here now? We have the iminium cation plus water, okay? We call that an iminium cation, okay? And it also applies to the secondary amine here, right? Now, when we had a primary amine, we had another proton we could remove off the nitrogen, right? We don't have that now. This is from a secondary amine. So there's no more hydrogens. We took one off here, okay? And a secondary amine only has the one hydrogen, right? That's a key thing about this being a secondary amine. So when we get to this point in the mechanism, we can't take that second one off. If we had a primary amine, we could. Where can we take off a proton? Well, it's right here. It's at this alpha position. Here's where the carbonyl was. This is the alpha position of the carbonyl. So we can take off a proton here, and we can use water, or we can use acetate if we're using that weak acid. You see we can push the electrons like that, and that will give us what? The double bond right there, and the lone pair back on there, and the neutral product. This also regenerates the catalyst. We only need a catalytic amount of the amine. I'm sorry, of the acid. We need a full stoichiometric amount of the amine. Catalytic amount of the acid is okay. In fact, we need to be at pH 5 to get the fastest rate. Okay, and that's what? We have enough acid to protonate this and to make this to occur. And plus we can help with the proton transfer here with a little bit of acid, okay? But if we have pH 1 or 0, why so slow? That's the question. What can occur here if you have an amine, okay, with strong enough acid? Right, this amine would just sit as the protonated form at what, low pH. If there's strong enough acid, it will just stay protonated as an ammonium cation. Is this nucleophilic now? Right, it's not a nucleophile, okay? So it's not able to participate in the reaction if the pH is too low. If the pH is too high, like I said, it will do an aldol reaction, will form an enolate and do some condensation chemistry with the carbonyls. We're not talking about that yet. So it'll give a different reaction. It won't give the regular imine-enamine reaction. So yeah, there's your issue with the pH. You need it to be just moderately acidic enough to protonate the carbonyl and allow for good nucleophilic addition. But if the pH is too low, too strong of an acid, then you protonate your amine and it's not a nucleophile anymore. So I think that was the key part of that. What happens here? It can reverse back. If you treat your enamine with water now and strong acid, so sulfuric acid and water will take it back to the carbonyl compound and back to the amine. It'll be protonated, it'll sit like that under the acidic conditions. To get the neutral amine, you'd have to neutralize that with a little bit of hydroxide, and then you could get that at the right pH. Anyway, it's adjustable that way. But on its own, that would be the reactivity. And I think we answered the rest of the questions on that worksheet, but check that sheet out. Let's go on now to reactions 5 and 6, the last two. And I like to do a little introduction here on these last two. We're going to talk about hydrates and acetals here in reactions 5 and 6. And to do that, I like to talk about a more advanced topic. This is going to be sugar chemistry. Okay, so here's a sugar. You'll learn this later. This is glucose, and glucose can be attached to another glucose molecule. And this disaccharide here, you'll soon learn the name of that. This is cellobiose, and you don't need to worry about that, but it's actually two glucose molecules hooked together. And how are these glucose molecules hooked together? Well, here's one glucose, here's another glucose, these six-membered rings, and you see a bunch of alcohols on each one of these carbons, these OH groups. And then you see an oxygen in the ring here, and this oxygen's on this carbon, and on this carbon's another oxygen. This carbon right here has two oxygens on it, okay? In fact, they're two ether oxygens. We're going to call that an acetal, okay? Anytime you can identify in a molecule a carbon with two ether oxygens on it, we call that an acetal, and that will be reaction 6 coming up. We also have a carbon over here that has two oxygens. Here's an ether oxygen right here and an alcohol. If you have an ether plus an alcohol on the same carbon, we call that a hemiacetal, okay? And what this means is this came from two glucose molecules. In fact, let's break this back apart. You can hydrolyze, we'll say, that position. And you'll get these two glucose molecules coming back off. This one over here will be the same. They'll have the two there that can come off there. And we'll see mechanistically how that goes if you treat with strong acid and water or an enzyme. and water. We'll learn later on that this will be a cellulase enzyme that will hydrolyze, we'll say, use water to break this bond to go back to the two glucose molecules. And that's about all I wanted to point out here. This acetal and this hemiacetal are two new functional groups, okay? They're compound functional groups, you could say. The acetal is two ethers on the same carbon, and the hemiacetal is an ether alcohol on the same carbon, okay? There's one other thing to point out here. You can break this hemiacetal linkage here, and what you'll have in glucose is an aldehyde right there. Now this looks kind of funny too. I just broke the ring right there, and I've got the alcohol there and the alcohol there. Oh, there's still one there. I've got 1, 2, 3, 4, 5 alcohols. This one right here can interact with the aldehyde and form this hemiacetal on glucose. Now, I know that might kind of seem confusing and everything right now. We'll have a whole chapter on sugars, and the key reaction there will be this hemiacetal for the simple sugars to form the ring form of the simple sugars. Then when we link sugars together, we'll link them together as acetals. So that's the main reason why we're covering these next two reactions. So an acetal, a carbon with two ethers on it, okay? And you can identify that carbon right there in this disugar. Then the hemiacetal is a carbon with an ether and an alcohol on it, on the same thing. And that's right there for the hemiacetal, okay? So two new functional groups to learn. That's okay. All right, let's get to the main event, reaction 5 here, which will be hydrate formation using water as a nucleophile. Hydration. So what does that mean? It means adding water, okay? So here's our carbonyl compound. And we're adding water, and this really seems like a simple reaction. And it's actually not productive synthetically, but it provides a lot of mechanistic understanding and a lot of understanding about reversibility of reactions. So what we're going to form here is the hydrate, which is a diol. It's a geminal diol, we're going to call it. Diol means two alcohols and they're on the same carbon, okay? So here's the element of water we just added across there. And mechanistically, you can already see how it's probably going to work. We got a couple steps there we'll need to talk about. But this is not favorable for most aldehydes and ketones. This is freely reversible. In fact, even if you can form the hydrate, in most cases, if you try to re-isolate this, it will reverse right back and lose the water. And that's actually an entropy effect. But we can look at the bonds that are being made here too. We're making a new sigma bond and a new sigma bond here, and we're losing a pi bond. So it kind of looks like it's favorable, but we're creating more order within the system. We're adding two molecules together. So actually the entropy is not favorable. We're ordering the system. So this is freely reversible when it forms a hydrate. Now notice this is different than the acetals and the hemiacetals that I just talked about. That's where we're going to have alcohols as nucleophiles. So why are we talking about this if this is free reversible? Well, again, like I said, it's a hallmark for the reactivity and the understanding. And actually, some aldehydes and ketones can favor the hydrate formation. We'll need to look at this. So at equilibrium, let's look at the percent hydrate formation for different compounds. If you have formaldehyde, for example, guess what? That one is 100% hydrate formation. What does a hydrate formaldehyde look like? Well, it's pretty simple. Looks like that. In fact, those formalin solutions used in biology labs are 100% this. If you try to isolate this back out of the water, it will reverse back and you can actually get formaldehyde, which is actually a gas on its own. So, but if you put it in water, it'll actually form the hydrate. It looks kind of funny. It has to do with the two hydrogens here being very small, so water can actually attack here and transfer the proton. We'll get to the mechanism in a second. But yeah, it is reversible. But at equilibrium, it's 100% hydrate. Okay. How about acetaldehyde? Well, now we have a methyl group and a hydrogen here. What does the methyl group do? Well, sterically, it blocks the approach of water. And also, inductively, via hyperconjugation, it's helping to stabilize the positive charge here on carbon. So it's less electrophilic. At equilibrium, though, how much hydrate do we have? 50% for acetaldehyde. But if we try to isolate the hydrate, and what would it look like? It'll look like this. It just goes right back to the aldehyde. Okay, so we can't isolate this. If we try to distill this or chromatograph it, it will just give up a water molecule and go right back to the carbonyl. What about this one? So now we have a tert-butyl aldehyde here. How about at equilibrium? How much of that? 19%. So sterically, the bigger group there is going to make it less favorable. How about a ketone, acetone, like we just showed in the first example? What percentage is that? Oh, 0.14%. Again, two alkyl groups donating inductively and sterically blocking the approach of water, so not favored. So those are the two factors, electronics and sterics there. How about this molecule? How about if we have trifluoro methyl groups there, hexafluoroacetone? Now we have inductive withdrawing groups here, right? What does that do to the electrophilicity of the carbon here? Right, 100% now. Hydrate formation. In fact, you can isolate the hydrate in this case if you've got strong electron withdrawing groups there. Same thing with chloral, which is the trichloro version of this. I'm sorry, it's the trichloroacetaldehyde version. This is also 100% for hydrate formation, again, because of the electron withdrawing group there. Yeah, and there's a couple others we could talk about. What I'd like to do now is the mechanism of hydrate formation. So let's see how that looks. And let's first do the mechanism under basic conditions. So here we are at high pH. pH will say high. So we have hydroxide present. We'll do three mechanisms. So this is why this is important here. This shows you mechanistically how to use oxygen nucleophiles with carbonyls. And it points out the reversibility. And what's the true nucleophile under basic neutral, and acidic conditions. Well, here's our nucleophile, and there's our electrophile, right? It's not protonated. So our intermediate would look like this, okay? And how do we get to the diol? Well, we've got water. So what can we do? Just grab a proton off there. Okay, there's the diol under basic conditions. Freely reversible, how would we reverse it? We take hydroxide, take a proton off. We'd have this intermediate. This would come back off, that would go back off, and you'd see the product there, okay? So the basic conditions is pretty simple there. Let's look at the rate for hydrate formation here. Looking at pH, just like we did for imines and enamines, 0, 7, and 14. Well, guess what? It's just the reverse here. It dips down at neutral pH 7. It's the slowest. It's fastest under strong acid and strong base conditions. And you can see why here, right? Strong base conditions, there's your nucleophile. There's higher concentration in the nucleophile. It's going to speed up that reaction. It's going to be very fast. So there's where we just talked about, okay? Let's talk about this now, the acidic range. That's going to be a little bit different. Now, if we've got strong acid, right, first thing we're going to do, pH 1 or 0, whatever, we have enough acid available to protonate the carbonyl, and we've got that. That's our true electrophile now under acidic conditions. What's our nucleophile? Well, it's not hydroxide, it's water, okay? So different nucleophile and different electrophile under the different conditions. But the effect is kind of the same, right? We're adding a oxygen nucleophile to the carbonyl. That part's the same. But make sure you're clear on what's the nucleophile under strong acid and what is the electrophile in strong acid. They're different than the basic conditions, right? So what do we get at this point? Well, we get this. Okay. Oh, 2 of them, not 3. Okay. Okay, we've got the protonated product. And how do we get that off? How do we get the diol product? Okay, there it is. And what do we need to do? Well, use more water, take the proton off, okay? Now, why does that occur very quickly under acidic conditions? Well, you have more acid here. You have more of this protonated. The electrophile is stronger now. Even though the nucleophile is neutral, under acidic conditions, fast reaction up here for basic conditions, but for different reasons, right? What about neutral? Very slow. Let's look at it here. The hydrate will form under neutral conditions, but let's see, how do we do it? Okay, it's a little bit different. We've got to involve a couple water molecules. I'm not going to involve any acid or base because the concentration of hydronium and hydroxide are very, very low at neutral pH. Let's do the hydrate formation just with neutral stuff here. So here we've got the 2 water molecules around the guy here. And let's see, how are we going to do this? Let's use 1 water molecule to take off a proton there. That will make these electrons available there. We can pull these electrons up here and then put those back on that water. Let's see, what will that go to? That will go directly to the hydrate. Let's see, we'll have water right there and there, okay? So here it is at pH 7, neutral. Why is this so slow? Well, it's a neutral nucleophile, and this is not protonated, okay? So it's not a good electrophile, not a good nucleophile, and it's a termolecular mechanism. You have to have the right geometry and collision for 3 molecules to come together. So you can see why that's slower than here, where you got a strong charged nucleophile, and here where you got a protonated electrophile, right? So neutral conditions, same product, the hydrate here. 1 water molecule's been added there. Protons have to reshuffle around to get to that. 3 different mechanisms for 1 crummy product, and the product's reversible that we don't care about? No, I'm showing you these mechanisms because these mechanisms will be important for the next one, which is what? Reaction 6. Yes, Aaron.
Couple of questions.
Oh, sure. No, we're just drawing it in the forward direction for the. And
you're okay if they do proton transfers groups together?
Yes, there are different ways you can do proton transfers. The key thing is getting the nucleophile on the carbonyl. But under basic conditions, you'd want to use which nucleophile? Hydroxide. And under acidic conditions, you'd want to use the protonated carbonyl. But like for here, you could have transferred this. Well, for the imine and enamine, maybe amine. I showed those intramolecular proton transfers. You can also transfer it to solvent first and then reprotonate it. That adds another step, but yeah, so there are some variations on these mechanisms.
I've got one more.
Okay, sure.
Talk about the questions being reversible. Do they need to be able to do the reverse mechanism as well as the forward?
Yes, yeah. And I think that's on quiz 5. Yeah. So I was going to let them be surprised by quiz 5. But that's due tomorrow, so make sure you're looking at that. Yeah. I think I have the reverse of one of the enamine reactions. But they're just the exact reverse of the ones we've drawn on the board. So if you can follow that in the backwards directions, then you draw your arrow in the other direction. But technically, each one of these steps are reversible. In fact, this isn't really favorable until you get to a real low pH here to protonate that there. And same thing here. This can reverse back. This can come off, you know. So yeah. In fact, all of these hydrate formations for simple aldehydes and ketones all reverse back if you try to isolate them, okay? But these 3 mechanisms are important to know, especially for acetals now. Let's look at reaction 6. We've got acetal formation. This is probably the hardest one. The mechanism's a little tricky here. And what do we have for reaction 6? We've got aldehyde or ketone, and we're going to use simple alcohols. And this is usually just ethanol or methanol here. And we're going to use acid catalysis. So HCl catalyst or sulfuric acid, but just catalytic amount. So our mechanism is going to have to account for that. And this is usually the solvent, the alcohol. So that's in excess. Now I won't always draw excess there or multiple equivalents. If it's the solvent, it's 55 molar in that. So it's very high concentration for the solvent there. And what we're going to form here is the acetal. Okay. So usually if this is methanol or ethanol, these are methyl or ethyl groups. And why is it an acetal? It's a geminal diether that you see right there for the product, okay? We're also going to form water that will be coming off there. You can kind of keep track of all the things. So we've got what? This needs to go on there twice. You got the 2 alkyl groups on there. And if you have 2 of these, you've got to get rid of what? H2O. So our mechanism will have to account for that. Let's look at some examples first, and then we'll do the mechanism. How about benzaldehyde and ethanol and HCl catalyst? Our product will be the 2 ethyl groups on there. And here's our hydrogen from where the aldehyde was. And it looks kind of funny. It looks like reading glasses of some kind there. But no, this is 2 ethers right on that carbon, so it is an acetal, okay, functional group there. And that is attained in a 92% yield, okay? And with the loss of water, can make that go very well there. Let's see, we got a couple other examples here. Here's acetophenone with methanol and acid catalysis. And you can go to the acetal with 2 methyl groups on there, okay? And that's a 78% yield. Usually aldehydes are a little better yielding than ketones. Oh, and let's do the cyclic one right away. So here's back to an aldehyde. And let's use ethylene glycol, which is ethane with 2 alcohols on it, and acid catalysis, and we're going to get the cyclic form of the acetal, okay? This product is very useful. The 2 ethers are right there in a ring. Sometimes that'll be used as a protecting group, and I'll show you how to use that in a second. What about the mechanism? That's the big thing now. And I'm going to show you that. Let's get some room here. It's going to be analogous to the acid catalyzed conditions for the hydrate formation. So let's see. Let's do it with this guy and methanol and HCl catalyst. Okay, so let's get our product up there first. So the two methyl ethers are right there. The acetal is formed. High yield in this case. What's the mechanism now? We're under acidic conditions, so it's going to be our true electrophile, right? The protonated form of this. So let's protonate our carbonyl. Okay. And there's equilibrium there. It can go back. But once we form enough of this and we're in the presence of what? Methanol, we can attack, right? And that will give us the alcohol up there and methanol with its hydrogen still on there. I'm not going to keep drawing this hydrogen here that's from the aldehyde, okay? You're going to have to keep track of that. That's right there, okay? So at this point, we've got one methanol unit on there. We need to convert this into a better leaving group by transferring the proton. And this was Aaron's question. So these proton transfers, can you do them intramolecular, or can we use methanol to take that proton off and go to the neutral thing and then transfer a proton in the second step to that? And the answer is yes, you can. I show this intramolecular thing just to save some space sometimes on the board. And Erin's nodding her head, so don't worry, we won't take off points if you do your quiz a little bit different. The key thing is, under acidic conditions, here's your electrophile, and your nucleophile is neutral at that point, okay? And now, you've got to transfer some protons to get to this point, hydronium ion there, and neutral methyl ether there, okay? This is the protonated hemiacetal, okay? And hemiacetals are often common, especially in cyclic molecules, like we saw with glucose, and we'll talk more about that later. The hemiacetal with these simple alcohols and aldehydes and ketones is almost always goes on to the full acetal, okay? But this, again, both of these steps would be reversible in principle. But if we have excess, we're using that as solvent, okay? And if we remove water or dehydrate this thing, we can help this along too. So let's go ahead and lose water right there. What do we get? The carbocation right there, okay? And there's water, okay? So if we remove water, we add molecular sieves, or if we're distilling this, removing that, we can make this equilibrium favorable here. We got a carbocation right there. Let's add more methanol. Got the neutral nucleophile again, and there's our carbocation. Notice this carbocation is resonance stabilized. Let's draw that resonance structure there. And you can attack either resonance structure here of this second electrophile. This is a new electrophile, right? So there's our electrophile. Here's more nucleophile. So let's go ahead and attack either one. It doesn't matter. We push the electrons over, then we get the neutral oxygen back there. So either one of these will give us the intermediate here. Okay. Yeah, those are all CH3 groups. Me means CH3. Sometimes I draw them out, sometimes I don't there. I wanted to emphasize that's the nucleophile we just added right there. That's not the product yet. What do we need to do? We need to take off this proton. How are we going to do that? Well, we've got excess methanol. Don't use chloride. Chloride's a much weaker base than actually methanol itself. Protonated methanol pK is about -2. Remember, the pK of HCl is -7. So you do not want to go to the stronger acid. You'd want to use this excess alcohol here to take that proton off. And you see, by doing that, what do you get? You get the product. There you go. There's your acetal product. Now, all these steps parallel what we've talked about here with hydration, right? Under acidic condition, we talked about protonating, the true electrophile being this. And for the hydrate, we used water as our nucleophile, but now we're in alcohol solvent, okay? So we can add the nucleophile there and give the product. Anyway, questions on the mechanism? Yes, they are reversible. And yes, you can kind of change up how you do the proton transfers. But the key things about what the electrophile is and what the nucleophile is, and this resonance stabilization here, loss of water is clear there, I think, in the mechanism right here. But man, how many steps is this? This is getting to be a little bit tricky, right? This is why CHEM352 is a little more complicated. None of your mechanisms from 351 were this many steps. How many steps? 1, 2, 3, 4, 5, if you count the resonance. 6 to here. 7 steps? Ouch. So that's why I emphasize that mechanism of hydration to show you, how the electrophile can be modified depending on what conditions we're under. For acetal formations, we'll stick to acidic conditions with simple alcohols, okay? But I will show you some variations here in how some things can occur. Well, we already showed you the cyclic variation, and let's show you why that one is important maybe. Let's see. So let's say you want to do a certain type of reaction. Let's use that cyclic acetal as a protecting group. Here's the reaction you want to do. You want to take this ketone that also has an alkyne in it, and you want to make somehow this alkyne now with a methyl group on the end. Add a CH3 group right there, okay? So how would you do that? Well, you could take this proton off using strong base, okay? But if this strong base is of the right character, it can add as a nucleophile here. A typical base to take off a terminal acetylene proton is actually a Grignard reagent. If you use ethyl magnesium bromide, yeah, that can take off that proton there and give you this, okay, with the rest of the molecule on there. And then what? Then we want to react with methyl iodide. And that certainly will work. Here we have a charged small nucleophile, primary leaving group here. This is SM2 reaction. Yeah, and that would work just fine. Well, what would be the problem here using ethyl Grignard as the base? Yeah, this could also add right here, okay? And that would give us a tertiary alcohol there. We don't want that. We want the free methyl ketone there. So what do? Well, first of all, we treat this with ethylene glycol. And maybe that's a term you haven't heard before. Ethylene you've heard before as a 2-carbon alkene there, but glycol is antifreeze. Ethylene glycol is used in your radiator. It boils at about 200 degrees Celsius and has a very low freezing point as well. So it's kind of an antifreeze, anti-boiling compound. It has a very wide range that it's a liquid there. So that's why it's used in car radiators. But we're going to use that with HCl, catalytic amount. And first we're going to form the protected carbonyl. Okay, so this is no longer a carbonyl now. This is an acetal. It's 2 ethers. Okay, it's like THF, the ether. Okay, in fact, we've used THF, this ether right here, for these Grignard reactions, right? So you can think of this as just like THF, this inert ether with an extra oxygen in it. This is not sensitive to strong base or strong nucleophiles now. This is tied up as a ether, a diether, this acetal. So it's inert now. Strong base conditions, strong nucleophile conditions will have no effect here. This is a regular stable ether, a 5-membered ring. But what we can do here is use strong base here. We can either use ethyl magnesium bromide, or we can use sodium hydride or sodium amide. If we use these strong bases with this ketone, we deprotonate here and give other products. So you can't use those either with this product. And the Grignard reagent that we're using to deprotonate here would be a nucleophile in that case, like we pointed out. But if we deprotonate there, you see we can get the acetylene anion and then we can treat with methyl iodide. And then how do we get the desired ketone back? Then we have to have a second step here where we treat with water and sulfuric acid. And this is the reverse of the acetal formation. Under the acidic conditions, we would protonate here. We would use the lone pair here to pop it open. You can do the rest of the mechanism. We then have a cation here that we could add water and eventually protonate there, and then go back to the product. So you can fill in, sorry about that, the mechanism for the rest of those. Oh, sorry. Let's look at a couple other examples here. We have this aldehyde in ethanol, catalytic acid. What would be our product? Again, the diacetal. What if we had this ketone with the cyclic ethylene glycol and the acid? Then we have this bicyclic product. And both of these are reversible, right? With water and acid, both can go back there. Okay. Good. So practice those mechanisms. You should be okay at that. Let's look at cyclic hemiacetals now. Cyclic hemiacetal. Now, what's a hemiacetal? Well, that's a carbon with an ether and an alcohol on it, okay? And they're favored when we have this type of a substrate. So here's an aldehyde with a carbon tether and then an alcohol within the same molecule. So let's imagine that as the nucleophile. And even under neutral conditions, this will most of the time favor this. And that's the hemiacetal of this. Now, mechanistically, we have to do some things here. We have to add in the nucleophile, and then we have to get that proton off that one. But let's see, at equilibrium, it's 6% the free aldehyde alcohol, and it's 94% this, the hemiacetal. Okay. Let's look at that. And why is this so favored? Let's see. Well, we're getting a new sigma bond right here at the expense of this pi bond. So you can already see how that's going to be favored. And plus, this is a 6-membered ring, so it's strain-free. So, or 5-membered rings are also favored for these cyclic hemiacetals. But this is reversible, okay? So we can see how that might reverse. And this is at equilibrium, but this is the major one because you're getting a sigma bond here at the expense of a pi bond. Entropically, though, you are ordering the molecule a little more. You're eliminating some degrees of freedom that the molecule might have. So entropy is actually not favoring this in this case. It's mainly the sigma bond formation here, even though it's a hemiacetal. Now, what you can take with this molecule is treat it with a small alcohol. So put it in ethanol or methanol here with a little acid catalysis, and what do you get? Well, the hemiacetal will go away, and what do you form? Yes, you'll form the what? You form the acetal. And this is now what? A mixed acetal. Now, why do I say mixed acetal? Because this ether here is a methyl ether. Here's our carbon with the 2 ethers on it. And then this ether over here is part of the ring. We're going to call this a pyran ring when we look at sugars later. But this is from a second alcohol added in here. And you can go through the mechanism of this and see it involves protonation here. and then loss of water right there. You can use the lone pair on that oxygen. So your electrophile in this case is actually this, and then the methanol can add, and you have to lose the proton off of here with another molecule of methanol, but you can see how that's going to go there. But these cyclic ones, if it's a 5 or 6 member ring, are strain free, and and that can be highly favored. Okay, let's look at sugar again and see what the cyclic hemiacetal of glucose is going to be. Okay, and again, we're going to have a later chapter on glucose, so you don't need to worry about this, but this is kind of a warning to you. Glucose is going to be a little bit complicated. It's a 1, 2, 3, 4, 5, 6 carbon molecule, and there's what, 1, 2, 3, 4 stereocenters. Each one of these is sorry, these are all hydrogens here. This is what's called the Fischer projection. These stereocenters will have RNS depictions to them. We won't worry about that right now. This is the open form of glucose. It's not the favored form. When you put glucose in water, it will form the hemiacetal form. But right now, let's just tip the molecule on its side. So kind of rotate it down, and I'll draw it as it's kind of becoming the ring form. And you'll kind of see where all the alcohols are. Here's a primary alcohol on the end here. Because it's tipped over now, you see it up here. Then you have secondary alcohol, secondary, secondary, secondary. I think there's 4 of those. And then, yeah, here's your aldehyde right here. Okay, that's just a different conformer of it. Let's go ahead and form what? The hemiacetal. So here's our nucleophile. Here's our electrophile. And this is under neutral conditions. This forms at pH 7. The major form now will be the hemiacetal form. Got to draw all the other alcohols in there. But that can be tricky to see. See, we've got to transfer a proton out here. Here's our aldehyde carbon. It was the aldehyde, right? That's going to be called the anomeric carbon later on. And what is this? Here's an ether right here, and here's an alcohol. 2 oxygens on that carbon. What is that? That's the hemiacetal. Yeah. So there it is. Over 98% of the time. Yeah, 99% of the time. In solution, glucose appears like that. It's a 6-membered ring. And what else do you see? You see equatorial and axial positions there. Most of the positions are equatorial, so we'll revisit that conformation. But yeah, don't worry about that. All you need to recognize here right now is where the hemiacetal is. And I think that's all you need to know there. Yeah, we already did that one. And let me see. Yeah, I think we covered that. So stay tuned next time for chapter 22 coming up, which will be carboxylic acid derivatives. And that will be our last topic before test 2 coming up. Yeah, so that will be chapters 19 through 22, test 2 coming up. So read ahead and good luck with quiz 5, and we'll see you next time. Very good.